Hello. So, in this video we are going to be introducing the fundamental theorem of algebra and sort of what it tells us and why that can be useful. So before we sort of dive in, a little bit of history. So the fundamental theorem of algebra was first sort of formally stated as a conjecture or as something that somebody would want to actually try to prove in 1608. But to be clear, it was actually considered in some form or another for more than 1,000 years before that. So this is one of those things that has been around for a very long time, and people have been trying to solve it for in excess of 1,000 years before eventually it was finally proved in 1806. So it was considered one of the great sort of moments in mathematical history when a proof for this was actually first sort of successfully created. It was almost proved a few years prior to that, but there were some holes in the logic that somebody had to sort of fill in. So it sort of has a little bit of an asterisk there. But people have been trying to solve it since the times of like the Roman Empire, and it took until after America was a country before we actually found a way to prove it, just to give some scale there. All right, so what is the fundamental theorem of algebra? In fairness, the actual statement is very long, very technical, and I will not put you through that. So instead, the general idea, essentially, what the fundamental theorem of algebra is, it says that if we have some polynomial, and that polynomial has degree n, then the polynomial has at most n real valued zeros and exactly n complex valued zeros up to multiplicity, or counting multiplicity. So I'm going to explain what that means in a minute. So the other thing it gives us is that complex zeros, meaning specifically the ones that aren't real. So these are things of the form a plus bi or whatever. We will, again, get into all the specifics here in a little while, other videos. But those zeros, they have to come in pairs, and specifically those have to be conjugate pairs or complex conjugates, and we'll get into what that means. But it basically tells us how many zeros that we should expect, and if we have these sort of not real zeros, it tells us a little bit more about those as well, okay? All right, so what do we mean by multiplicity? So the easiest sort of way to do this is to see an example. So let's say we have some p of x, we factored it, we have x plus 1 to the 1. You don't usually have to write the 1, but I'm doing that to sort of make this easier to see what's happening. X minus 1 to the 2, x minus 3 to the 5, okay? Then there's two ways of talking about the zeros: distinct zeros and zeros with multiplicity. The distinct zeros, that's just the x minus 1, the x is positive 1, and x equals 3. So there's three distinct zeros, right? And we get those by setting each of these things equal to 0 and solving. We get the negative 1 from the first thing, the 1 from this second one, the 3 from the third one, okay? Now, if we're looking at the zeros counting multiplicity or with multiplicity, what that means is that we count each of these things, even if they're the same number, separately. So we have one of these x plus 1 factors, which gives us x equals negative 1 once. But this x minus 1, we have two of those. So that we get an x minus 1 and an x minus 1. That would give us x equals 1 twice, one for each of those factors, which is why we have it listed twice down here, right? And this x minus 3, that's showing up 5 times. So we have x equals 3 5 times down here, okay? So when we say counting multiplicity or with multiplicity, what that means is that we're writing out those sort of identical factors. If we get more than one, we're writing them out more than once. And so here we have that p of x is 8, has 8 zeros if we're counting multiplicity, as opposed to having 3 zeros if we're just looking at distinct zeros, right? Not having copies sort of written out separately. Now, as a sort of example to why this works with the fundamental theorem of algebra, if we multiplied this out, which I'm not going to do because it would be huge and make your brain hurt and there's no reason, but if we were to multiply this out, it would turn out that this thing is a degree 8 polynomial. And so that's why it turns out to have 8 zeros counting multiplicity, even though it only has 3 distinct zeros. Okay, so fundamental theorem of algebra tells us it has some number of zeros equal to the degree if we allow the duplicates to be counted sort of on their own instead of only looking at distinct values. Okay, and again, complex ones are sort of another thing. We're going to go through that separately. Here, these are only real zeros. Okay. All right, so what do? Well, we introduced the fundamental theorem of algebra, which the actual statement is sort of a little crazy, but for the sake of this class, it basically tells us that the number of zeros we have, if we count complex ones and we count multiplicity, that's going to be the degree of the polynomial. The real ones is some subset of that, and so it has sort of at most the degree of real zeros, could be equal. And we know that complex come in what are called complex conjugates, but we're going to sort of deal with that as a separate thing, okay? And we gave a quick example, just to see what we mean by multiplicity, okay? So that is that.